I found the UNet architecture useful for many applications I've worked on, and this is one of the most important and foundational neural network architectures of computer vision today. So in this video, let's dig into the details of exactly how the UNet works. This is what a UNet looks like. I know there's a lot going on in this picture. It's okay. We'll break it down and step it through one step at a time. But I want to quickly show you the final outcome of what a UNet architecture looks like. And this, by the way, is also why it's called a UNet, because when you draw it like this, it looks a lot like a U. But let's break it down and build this back up one piece at a time, so we can make sure we know what all of the things going on in this diagram actually are doing. These ideas were due to Olaf Ronneberger, Philip Fisher, and Thomas Brox. Fun fact, when they wrote their original UNet paper, they were thinking of the application of biomedical image segmentation, really segmenting medical images. But these ideas turned out to be useful for many other computer vision semantic segmentation applications as well. So the input to the UNet is an image. Let's say it's H by W by 3 for 3 channels, RGB channels. I'm going to visualize this image as a thin layer like that. I know that previously we had taken neural network layers and drawn them, as 3D blocks like this, where this might be, right, sort of H by W by 3. But in order to make the UNet diagram look simpler, I'm going to imagine just looking at this edge on. So all you see is this, and the rest of, this is hidden behind this dark blue rectangle that I've drawn. And so that's what this is. The height of this is, the height H, and the width of this is 3, right? Which the number of channels, the depth is 3, so it looks very thin. So to simplify the UNet diagram, I'm going to use these rectangles rather than 3D shapes to illustrate the algorithm. Now, the first part of the UNet uses normal feed-forward neural network convolutional layers. So I'm going to use a black arrow to denote a convolutional layer followed by a ReLU activation function. So the next layer maybe looks like that. We've increased the number of channels a little bit, but the dimension is still height by width by a little bit more channels. And then another convolutional layer with a ReLU activation function. Now, we're still in the first half of the neural network. We're going to use max pooling to reduce the height and width. So maybe you end up with a set of activations where the height and width is lower, but maybe it's thicker. So the number of channels is increasing. Then we have 2 more layers of normal feed-forward convolutions with a ReLU activation function. And then let's apply max pooling again. And so you get that, right? And then, repeat again. And so you end up with this. So far, this is the normal convolution layers with activation functions that you've been used to from earlier videos with occasional max pooling layers. So notice that the height of this layer, height and width, is now very small. So we're going to start to apply transpose convolution layers, which I'm going to denote by the green arrow in order to build the dimension of this neural network back up. So with the first transpose convolutional layer or transconv layer, you're going to get a set of activations that looks like that. In this example, we did not increase the height and width, but we did decrease the number of channels. But there's one more thing you need to do to build a UNet, which is to add in that skip connection, which I'm going to denote with this gray arrow. What the skip connection does is it takes this set of activations and just copies it over to the right. And so the set of activations you end up with is like this. The light blue part comes from the transpose convolution, and the dark blue part is just copied over from the left. To keep on building up the UNet, we are going to then apply a couple more layers of the regular convolutions followed by a ReLU activation function, so denoted by the black arrows like so. And then we'll apply another transpose convolution layer. So green arrow. And here we're going to start to increase the dimension, increase the height and width of this image. And so now the height is getting bigger. But here too, we're going to apply a skip connection. So there's a gray arrow again. I'm going to take this set of activations and just copy it right there over to the right. More convolutional layers, another transpose convolution, skip connection. Once again, we're going to take this set of activations and copy it over to the right. And then more convolutional layers, followed by another transpose convolution, skip connection, copy that over. And now we're back to a set of activations that is the original input image's height and width. We're going to have a couple more layers of a normal feed-forward convolutions. And then finally, to take this and map this to our segmentation map, we're going to use a 1-by-1 convolution, which I'm going to denote with that magenta arrow, to finally give us this, which is going to be our output. The dimensions of this output layer is going to be h by w, so the same dimensions as our original input, by num classes. So if you have 3 classes you're trying to recognize, this would be 3. If you have 10 different classes you're trying to recognize in your segmentation map, then that last number will be 10. And so what this does is for every one of your pixels, you have h by w pixels, you have, an array or a vector essentially of n classes numbers that tells you for that pixel, how likely is that pixel to come from each of these different classes. And if you take a argmax over these n classes, then that's how you classify each of the pixels into one of the classes, and you can visualize it like the segmentation map shown on the right. So that's it. You've learned about the transpose convolution and the U-Net architecture. Congrats on getting to the end of this week's videos. I hope you also enjoy working through these ideas in the program exercise. Next week, we'll come back and talk about some specialized architectures for face recognition and for neural style transfer, where you get to create some really interesting artwork using neural networks. Have fun with the program exercise, and I look forward to seeing you next week.